Welcome, everyone. Today we are exploring a game-changing feature in Snowflake, Cortex Complete Structured Outputs. Let's get started and learn how to guarantee precision in our AI applications. Let's begin by defining what Cortex Complete Structured Outputs actually means. When building AI applications, relying on plain text responses can be a nightmare for application integration. To solve this, the AI complete function lets you supply a JSON schema or SQL type literal that completion responses must follow, producing structured output. This fundamentally changes how we interact with LLMs. Instead of begging the model to format things nicely, AI complete verifies each generated token against your structured output definition to ensure that the response conforms to your exact type structure. Why is this so important? Because structured output reduces the need for post-processing in your AI data pipelines and enables seamless integration with systems that require deterministic, predictable responses. Take a look at this flowchart, which illustrates the structured output pipeline. On the left, your application sends a user prompt to the AI complete function. But instead of just generating text blindly, the model enters a strict verification phase in the center. AI complete verifies each generated token against your structured output definition. If the token aligns with your JSON schema, it is accepted, eventually producing the perfect structured JSON output on the right. If a token violates the schema, the system rejects it at the generation level, guaranteeing that your downstream application never receives a broken or malformed payload. If you are a data engineer comfortable with SQL, Snowflake provides a native, streamlined way to enforce structure, type literals. Type literals allow you to define structured output for AI complete using SQL types, taking advantage of Snowflake's built-in mappings between SQL and JSON types. How do we use them? It is straightforward. You begin your type literal with the type keyword and use a SQL object as the top-level type. Inside that object, the properties can be any SQL type with a supported mapping to JSON, like arrays or strings. It's a highly efficient way to get structured data without writing complex JSON files. However, keep in mind a key constraint. Type literals are supported only for the single-string text prompt version of AI Complete. If you are doing complex, multi-turn chat arrays, you will need a different approach. This diagram breaks down the structure of a SQL type literal request. You start your SQL query and assign the response format parameter to the type keyword. From there, you define the root as a SQL object. Inside this object, you declare your desired keys and SQL types like a note as a varchar, an items count as a number, and a price as an array. When the model processes this, Snowflake uses its built-in engine to automatically map these SQL types to their JSON equivalents, cleanly outputting the generated JSON response at the bottom. It bridges the gap between relational database types and modern document structures flawlessly. While SQL type literals are great for quick tasks, enterprise applications often demand total precision. For more control over structured output, use a JSON schema as the value for response format. The supplied JSON schema defines the structure, data types, and constraints that the generated text must conform to, including required fields. By using the required field in the schema, you instruct the LLM that it absolutely must extract certain data points, and Complete will raise an error if a required field cannot be extracted. As a senior architect, you must also be aware of model-specific nuances. For instance, if you are using OpenAI models, the additional properties field must be set to false in every node of the schema, and the required field must contain the names of every single property in the schema. Let's examine the anatomy of a JSON schema object through this class diagram. The root object, JSON schema, must be defined with a type of object. Within it, we define our properties, such as name, age, and a Boolean isAdult flag. Notice the required array at the root level. This is where you explicitly list the fields the model cannot ignore. Furthermore, to ensure compatibility across all models including strict OpenAI requirements, you should explicitly define additional properties as false. By passing this highly structured blueprint into Cortex, you eliminate hallucinated keys and ensure your data pipelines receive exactly the payload format they expect to process. Let's pivot to how data scientists and backend developers can leverage this in Python. Writing raw JSON schemas by hand can be error-prone. Thankfully, structured output is supported in Snowflake ML Python version 1.8.0 and later. Instead of writing raw JSON, you can use Pydantic, a highly popular data validation library for Python, to define a schema for the response format. You define your data classes normally in Python, and then simply convert the Pydantic model to a JSON schema using the model JSON schema method. Once converted, you pass this JSON schema directly to the complete function as the response format argument. This creates an incredibly elegant developer experience where your Python backend classes are automatically synchronized with the exact JSON payload the Snowflake LLM generates. This sequence diagram walks through the Python developer workflow. The developer starts by defining a standard Python class using Pydantic, like a person object with name and age. The Pydantic model automatically generates the underlying JSON schema. The developer then invokes the Cortex complete function, passing the schema in the response format parameter. Cortex securely transmits both your prompt and the strict schema to the LLM. The LLM processes the request and streams back a strict JSON response. By the time it reaches your Python application, you have a perfectly formatted, validated dictionary ready for immediate use, completely bypassing tedious text parsing logic. To master Cortex Complete, you need to understand how to optimize the model's adherence to your schema. While complete structured outputs does not usually require a prompt to enforce JSON formatting, task complexity can significantly influence the ability of LLMs to follow a JSON response format. For simple tasks like entity extraction, just using structured outputs is enough. However, for medium complexity tasks that require reasoning, we recommend adding respond in JSON in the prompt to optimize performance. For highly complex, open-ended reasoning tasks, you must use powerful models like Claude 3-5, Sonnet, and explicitly detail the schema you want in the prompt itself. Additionally, provide detailed descriptions of the fields within the schema to be extracted so that the model can more accurately identify them. Finally, for the most consistent results, set the temperature option to 0 when you call complete, regardless of the task or model. This decision tree guides you on how to handle different task complexities to ensure perfect JSON adherence. Starting from the top, you evaluate your task. If it is a simple task, like basic extraction, no explicit prompting is needed. If it is a medium task involving some rationale, route down the middle and add respond in JSON to your instructions. If you are executing a complex task, like scoring call transcripts, you must use a top-tier model like Sonnet 3.5 and actively describe the schema within the prompt. Regardless of which path you take, all workflows converge on the golden rule at the bottom: set temperature equals 0. This ensures the model behaves deterministically, providing reliable, application-ready outputs every single time. As enterprise architects, we must strictly manage costs. Let's discuss the financial mechanics of using structured outputs. The excellent news is that Cortex Complete Structured Outputs does not incur additional compute cost for the overhead of verifying each token against the supplied JSON schema. The validation engine running in the background is essentially free. Your compute cost is based purely on the number of tokens processed. However, you must design your schemas thoughtfully. The number of tokens processed and build increases with schema complexity. In general, the larger and more complex the supplied schema is, the more input and output tokens are consumed. Specifically, highly structured responses with deep nesting, such as hierarchical data arrays, consume a larger number of tokens than simpler, flat schemas. Keep your schemas as flat and concise as possible to optimize your token budget. Look at this cost breakdown diagram to understand what drives your bill. On the left, we have the two primary cost drivers: input prompt tokens and generated output tokens. These combine to form your total compute cost. Now, look at the bottom node representing token verification overhead. As indicated by the dashed line, this operation adds 0 additional cost to your bill. However, observe the top node, a deeply nested JSON schema. Because the schema itself must be passed as input, and the resulting complex JSON syntax requires more characters to generate as output, a complex schema inherently increases both your input and output token counts. Efficient schema design is therefore a direct mechanism for cost optimization. Let's apply this to a real-world, high-value enterprise use case: support ticket extraction. Imagine a customer submits a sprawling, messy paragraph complaining that their mobile app crashed while they were trying to buy running shoes, and they include their home address in the text. Traditionally, extracting this data requires complex natural language processing pipelines. With Cortex structured outputs, we simply pass the customer's text to AI complete alongside a JSON schema that requires specific objects like customer, issue, and cart. The model reads the narrative and outputs a pristine JSON payload, cleanly separating the customer's shipping address into city, state, and zip code, and calculating the cart items and prices. To make this pipeline completely bulletproof, we use the try-complete function rather than complete. This ensures that if the model encounters an unparsable edge case, it gracefully returns null instead of failing the entire automated pipeline. This sequence diagram illustrates the automated support pipeline in action. It begins with the raw, unstructured complaint text originating from the support tickets database. This text is fed into the try-complete SQL function. The function bundles the messy text with our strict JSON schema and sends it to a highly capable model like Claude 3.5 Sonnet. The model does the heavy semantic lifting, extracting the requested entities, and returns a fully validated JSON payload. Because the output is guaranteed to match our schema, it flows perfectly into our analytics dashboard, instantly revealing the parsed address, cart contents, and the severity of the issue. It's a frictionless data transformation. In our final slide, we address advanced schema architecture using JSON references. As your AI projects scale, you will find yourself defining common objects, like an address or a price, repeatedly across dozens of different prompts. This causes bugs and massive technical debt. Schema references solve practical problems when using Cortex complete structured outputs. With references, represented by the $f syntax, you can define common objects once in a $defs block and then reuse them throughout the schema. This means when you need to update validation logic or add a field, you can change it in one place instead of in multiple locations. Ultimately, using references reduces coding effort, reduces bugs from inconsistent implementations, and creates cleaner hierarchies that better represent entity relationships. Master this, and you master enterprise AI engineering. Thank you for joining me. Please like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. Our final diagram visualizes the elegant modularity of JSON references. At the top, we have our root schema. Inside this root, we define a $defs dictionary, which acts as a library containing our standard definitions for a price object and an address object. Now, when we build out the rest of the schema such as the cart items array or the customer shipping profile, we don't rewrite the properties. Instead, as shown by the dashed lines, we simply use the $f keyword to point back to our central definitions. This modular approach helps you manage technical debt while maintaining schema integrity as your projects grow more complex. Don't forget to visit quicktechie.com to accelerate your cloud journey.